I've got bad news for all of you. So loud. I forgot to it's a secret. I forgot to pin my video all of last week. So because of that, and I didn't remember that, anytime somebody said anything in class, their face flashes up on the screen. And I posted all those videos on YouTube without even checking them. And they're still there. And I just thought about it this morning, which means that I've got to go back through and take them all down. And they've already been watched. So, it's going to be bad news for me. But I pinned my video this time, so it won't work out. But don't go watch. Nobody watched my videos anyways, except for those loyal watchers that used to be over in the Central African countries. But they don't do that anymore. Anyways, long story longer. They disconnected the battery. So once I disconnected the battery and they isolated the two capacitors, so their charges remained on them. Then in the problem, they said they flipped one of the capacitors and connected them together. So flipping one of these capacitors effectively just takes and makes this one positive, this one negative, and that's now the hole, and that's the electron. That's flipping them, right? So when I connect these, what's going to happen is this electron is going to fill the vacancy that's available there, and one of these electrons is going to fill the vacancy that's available there. Now, in this example, I only made two charges on one and one charge on the other. But what this is going to do is it's going to cancel out effectively whatever amount of charge was on the smaller capacitor and take it away from the amount of charge that was on the larger capacitor. But what's left will still be an unbalanced charge that now represents the total charge in this new circuit. I don't know how much charge is left, and I don't know how much will go to capacitor 1 or capacitor 2. I don't know that. I just know that after you cancel out those charges, whatever's left is going to be spread out on Q1 and Q2. How it gets spread out? Well, that's going to be defined by whatever it takes to equalize the potential on those capacitors. So, not knowing what the problem is, we could work a sample question and then you could do yours for homework. So let's work one that's like this and see how the numbers would work out. And to make it somewhat straightforward, let's have our capacitor 1 be, let's go with 15 microcoulombs, and capacitor 2 be 30 microcoulombs. And let's use a 9-volt battery. So your first job is to set up a circuit where both capacitors can be charged to the 9 volts. And you need to figure out, I don't know why I put microcoulombs there. That was just me being at home and maybe not, my full physics self, but that should have been microfarads. I don't know why I put C there. I really don't. I don't. Sorry. I know Alex is very disappointed in me. Look at that look on his face. He's terribly disappointed in me. I understand. And I just saw Ivan look a little closer at his computer to see if actually it was Alex looking disappointed. It was. It totally was. So microfarad, 30 microfarad. There we go. So take a minute and please calculate the charge on each of the capacitors. This is pretty straightforward. So I'll give you guys a second, and I'm going to pause for the cause and drink a little bit of coffee from my Haunted Mansion mug. See, today I get to feature a new mug because me, like Joey, I'm at home. But I don't fill mine with sadness like you. I fill it with coffee.
Yesterday I got coffee from Dunkin' because it was free.
Oh, so you had a happy day yesterday.
Not necessarily, but yes.
That makes my heart happy. I mean, the coffee probably is not doing any favors to my heart, but yeah. All right, that should be enough time. So let me pick on somebody. Let's go with Xavier. Can you give me the charge on one of these capacitors?
Q1 is 135 microcoulombs.
135 microcoulombs. Thank you very much. And Darnell, can you give me the charge on the other one?
The other one's 270 microcoulombs.
Thank you. So, any trouble with that? All right, so that's pretty straightforward. Glad you guys could do that. Please notice, I think obvious, the larger capacitor has more charge for the same voltage. So that's what we kind of want to see. So now we're going to isolate the two and take away the battery. And apparently one of the wires, although that was unnecessary. So this is the positive side, this is the negative side, positive side, negative side. And now we're going to flip it. So effectively what's happening is when I flip it, I'm making the charge negative. You can think of it that way, that suddenly when I flip it, this has a negative charge, not a positive charge. That's not a great way to think about it, but it is really what's happening. Because we call the charge kind of this holistic value, that this is the charge on the capacitor, but truthfully, we know that there's a separation of charge. There's positive and negative. So by flipping it, we're inverting the charge. So putting them together means that we suddenly have a total charge of 270 minus 135, which is going to be a total charge of 135 microcoulombs. That becomes the total charge for the circuit. You know, all those holes were filled by the spare electrons. The problem is, the moment I do that, the capacitance of each capacitor is still the same. And charges are going to move back and forth after they equalize the ones that are opposing. I will have this amount of charge left over that didn't have a place to go. Now, it's not going to set up to be equal charge on both plates because charge gets driven based on electric potential. What is going to happen is the electric potential across each plate is going to equalize because they're in parallel. So if that didn't work out, the electric potential will drive charge until it does. That's what electric potential does. Electric potential creates, as we've seen in the past, a landscape, a hill. So if one of these is at a higher potential than the other, the charges have to roll downhill until they equalize. So we need to ensure that at this point we understand this is the total charge we have, but there will be Q1 on this and Q2 on that. And they're going to equal that total. At the same time, the voltage on each capacitor has to be the same, which means Q1 over C1, which is voltage, has to equal Q2 over C2 because they have to be the same. I know the capacitance. This will give me a method to figure out what the charge is on each capacitor, and eventually a method to figure out what that total voltage is too. So I hope you see what that method is going to be. I am going to eliminate charge from one of these equations, and I think probably I'll eliminate it from here by setting Q1 equal to C1 over C2 Q2 and plugging that in. So in the case of this problem, flip that sucker over there. I'm going to get C1 over C2 Q2 plus Q2 equals 135. So Right, C1 was the smaller one, wasn't it? So I got Q2. Is that 90? Not bad for an old guy. Still got some smarts. That means Q1 has got to be 45. But now you can figure out what the voltage is. And I'm a little interested in this, so we'll do that 90 microcoulombs divided by 30 microfarads equals 3 volts. So basically just wiped out 2/3 of the energy we had stored.
Mr. Sheldon, can I ask you a question?
Can I say no?
You said that the problem finishes when the voltages are the same because they're in parallel, but I don't see how they're in parallel. I see them like they're in series because it's a negative plate connect to the positive plate other. Basically, how are they in parallel in this scenario?
It's a good question. I'm trying to figure out the right way to ask it or the right way to answer it. What makes these in parallel? Especially since, and let me go to another page if you don't mind, Alex. Especially since it shouldn't be electrically different to draw these two things. Oops. Right? How do I in all honesty say to you that both of these represent something that's in parallel? Now, the truth is, if I use the word parallel, I'm probably using it out of context. When it was connected like this to the battery, it was parallel. You see why that's parallel, correct?
Yes.
And that's series, right? Now, when I disconnected and reconnected the circuit up, I don't think either of these can be construed as series or parallel. I don't think we can do it like that. I said that charges will have to flow until the potential is the same on both of them. And that's what I should have said. If that's not how I said it, I'm sorry. But the potentials have to equalize, because if they didn't, if one of these is at a higher potential than the other, then by definition, it's going to push charge until the potentials are the same. Because if one's at a higher potential, that means by definition, the higher potential is going to create an electric field. That electric field is going to apply a force to charged particles, which means the charges are going to flow until there's no longer a force on those charged particles. And the only way there can be a net force of 0 is when the electric field becomes 0. And that's only going to occur when the electric potential is the same. So and I'm going to call this the low plate, the low potential side. The high potential side, these two can't be at different potentials without there being a flow of charges between them then. And that would be true there as well. Well, although I drew that backwards. The low potential sides, the sides that are the negative sides, they're going to have a flow of charge. If one of those had more charges than the other, not more charges, one of them was at a higher potential than the other, there would have to be a flow of charge because there's going to be an established electric field between them. So effectively looking at this. Oh, I don't want to do that. I'm really trying to look at just this one for a minute. And imagine if we can. So I'm trying to answer your question, and unfortunately, you asked a question that's a good one. I want to answer it thoroughly and clearly, but I'm having to make up a way of communicating it while I'm answering it. So that's why I'm kind of bumbling around a little bit. But just imagine for a moment that after you connect these up, the instant that you connected them, if the potential difference between here and here was 15 volts, and the potential difference between here and here was 10 volts. And notice I'm drawing the arrow purposefully because that's how we connected them. The charges are going to move so that these two are at the same potential and these two are at the same potential. If they're not, if this and this are at different potentials, then everywhere in this wire, an electric field will be established to drive charges, to push on charges. So if Y was at if this plate, the Y2 plate, is at a higher potential than the Y1 plate, which they are right now, then charge will have to go in this direction, which is going to lower this potential, dropping it maybe to 14, and increasing this one, maybe increasing it to 11 volts, because the electric field is there. Well, now the playing field got a little bit closer, which made the electric field between these two get smaller, but there's still an electric field between these two, which means it's still going to push on charges, which is going to mean I'm going to get more charges leaving this plate, dropping this to 13, increasing this to 12. And I'm making up the 12 and the 13 just to indicate that as long as there is a difference in potential, there has to be a flow of charge because of the force on the charged particles. Now that flow of charge is going to increase the potential of one of the plates and decrease the potential of the other plate. And that's going to continue to occur until there's no longer an electric field to push in the charges. Right, Dylan's mom? Yeah, we saw that. Now, this will occur until the two potentials are the same. At that point, the electric field disappears, and there's no longer a force in the charged particles. It doesn't matter how I've connected it. I've created a conducting pathway that allows for the flow of charged particles, and they will be driven by a change in potential. So it's not about series and parallel. It's about the fact that the two plates that are connected together, these two are connected together, and these two are connected together. Those two plates have to go to the same potential, those two couples of plates. And they will continue to drive charge until they do, because they are electrically connected together by a conducting pathway. So we just happen to have a condition where these plates were, say, the negative plates, and these are the positive plates. So we have a difference in numbers of positive charges on one and difference in number of negative charges on the other. But the potentials that they're at will drive the flow of charged particles until they're equal. It's easier to see that if I draw it this way, that if this is at 15 volts and this is at 10 volts, we can assume the bottom, the base charge is 0. And that flow of charge only occurs, say, up here. But it's actually occurring on both sets of charges because there is no zero plate. There's just a difference in potential on one side compared to the other. I don't know if I've answered that question well enough for people in class to understand it, but that was my best attempt. Because, I mean, the truth is, Alex, this is not where I wanted to go today. What if we had this? And I think this would be an excellent practice. I've never seen this question on any exam, but it would be interesting to know what the answer is. I don't know that I could tell you what the answer is right off the bat without having to sit and think about it, but I'm trying to come up with an example that might exaggerate this phenomenon. What if we repeat your question? But this was my circuit. So I have, say, my 9 volts here, and I have my 15 microfarad here, and let's say a 30 microfarad here and a 30 microfarad here. Now, first, this is kind of the problem I wanted to do today. I wanted to do a redux example where we reduce this by piecewise reduction and then try and solve it by going back through the circuit. But I think it'll allow us to ask an interesting question when we're done. Okay? So let's first start by doing that, because I need people in the room who are not invested in the question you asked to practice this. I want you to do a piecewise reduction of this circuit so we can figure out the charges and potentials on all the plates. That means taking the circuit and reducing it to an ever simpler circuit. So, and I'm really speaking to the folks who did not have a physics class last year, because that's what we're talking about here, piecewise reduction. Taking our complicated circuit and reducing it in steps to a simpler circuit. You're going to follow the rules that we established for series and parallel, which should be easily established here because we do have a driving electric potential. So the first thing to do is to recognize that you have to work from the inside out. So I've created the roadmap for you. And by roadmap, I'm talking to all the people who don't or did not do this last year. Piecewise reduction looks for examples of series and parallel and uses the rules we established for series and parallel to replace a system of capacitors with a single equivalent capacitance. So the first thing I see is I see one that's in series. And the rule for series requires you to add the inverses. I've made the numbers relatively easy, so it wouldn't be too hard for you guys to work this out and recognize that the total here is 15 microfarads. So there's my equivalent circuit, meaning that to the battery, to the 9 volts, this circuit would perform the same way from the standpoint of the battery. The battery would deliver the same amount of charge. So that's my first stage reduction. My second stage reduction would be to take that circuit and reduce it down to a single resistance. I have two capacitors that are in parallel this time. So to reduce them, I merely add the individual capacitances, which gives me my 30 microfarads. That is a stepwise reduction of the circuit. Any questions about stepwise reduction? It's my expectation from this point forward is I don't have to do practice like this again. Now, going backwards, we apply some different rules, but going backwards means figuring out the charge and potential for each of the capacitors by applying more or less our one rule and just applying it over and over again. So in this case, I'm going to apply my 9 volts to my 30 microfarads and do my division. 30 divided by 9. I don't know what that is. Is that the 270? Microfarads? No. Microcoulombs? Is it really 270? Okay, I have to believe you. So here, when we go back a step, we have to decide which of these two numbers that we've just gotten is most applicable to the scenario that we're returning to. And so for you guys who are new to this, it's a pretty simple rule. Now, the truth is you're all new to this, but we did this last year for resistors, and it's very similar. When you go back a step, if you're going back to a system that's in parallel, you apply the voltage to each of the items. They all have to have the same voltage. If you're going back to a system that's in series, you would apply the charge to both objects. Because capacitors in series all have the same charge. So we've applied the voltage to each object. So now we can go and figure out the individual charges for each one. So I think we're looking at 135 microcoulombs on each. Interesting thing, you should be able to check your work. There's a finite amount of charge. So when you do this, you should be able to see that the charge sum should equal what you had before. So like I said, there's a finite amount of charge. We can't add any or take any away, so you should have equal amounts. Now, the fact that they're both 50 microfarads made this somewhat easy, but it is a way to check your work. If they were different, they should still add up to equal the total. Now, we have effectively solved that capacitor because it is the same capacitor in both circuits. But the other capacitor was actually made of a system of two capacitors that were in series. When I'm returning to a system that's in series, I take the charge and I apply it to each of the objects in series. So it's 135 microcoulombs on that capacitor and 135 microcoulombs on that capacitor. Now, the final step is to actually figure out the voltage. And again, you're just going to do a little bit of division to figure out that this is 4.5 volts. This is 4.5 volts. Which shouldn't be a surprise. We had 9 volts before. I should still have 9 volts. Now, that is the process of doing piecewise reduction and solving a circuit. And I think that once you've done this a couple times, it becomes very simple. We're going to need to be able to do this for our series circuits and our capacitive circuits. I'm sorry, I meant to say resistor circuits and our capacitive circuits. But is there any questions about this piecewise reduction process? Now, this only works if you have an all capacitor system or an all resistor system. It's the only time this stuff works. The moment we have things where we're going to have mixtures of capacitors and resistors, we can't do this. This process is Kirchhoff's laws. That's really all it is. But we're using some simple things we derive from Kirchhoff's laws, like the fact that capacitors in series have to be added the inverses, and capacitors in parallel, we add them straight across. But I want to be really clear that we can do this as long as we have clear series and clear parallel. But now we need to speak to Alex's question, and I think it's an important question. What would be the result after having done all of this and having my circuit the way it is right now? What would be the result of taking that away? I think it's a good question, because what's in series, what's in parallel any longer? And the answer has to remain that charges will be driven based on any potential difference between a conductor. Now, if we think of this system, I don't think anything would happen if I was to open up the switch and just take the battery away. These bottom capacitors, or this bottom capacitor plate and this bottom capacitor plate, had to have been at the same potential at the start when the battery was there. Right? You following what I'm saying there, Alex? Because both sides of that capacitor were connected to the negative side of the battery. And these two also have to be at the same potential, because both of those plates were connected to the positive terminal of the battery and were raised to that potential. So they're at 9 volts. So the only thing is this plate, now how do I do this? Is this plate and this plate at the same potential? Because if they're not, charges will flow. And if this bottom area here was 0 and this was 9 volts, then from 0 to the top plate was an increase in potential of 4.5 volts. And from here down to this plate is a decrease in potential of 4.5 volts. I'd say this area right here has to be at 4.5 volts. And therefore, the whole area is at 4.5 volts and no charge would flow. Because it's going to still be driven by changes in potential.
So then if the capacitors were like different values, there'd be different voltages, so there would be a flow once you take the battery out. Okay.
Now, the real question would be, and I don't have the answer to this, and I'm not trying to throw you guys to the wolves or anything, is the problem that we were dealing with, where this came from, was that a change was made to the orientation of one of the capacitors within the circuit. You know, they took and flipped over one of the capacitors. I don't know what would happen under that situation. We would have to work out what could happen. Like if we just took this capacitor and flipped it around, well, we would suddenly change the electric potential of everything in the circuit relative to each other. So charges would flow in that system, and they would flow until the plates that were connected together were all at the same potentials individually. So, and like I said, I'm not trying to make up a problem that I would ever give you, because I don't think this would ever be on the test. It's never been on the test before, so nobody's asked it before, you know, when it had more than 2. But if we had the situation that we just described, I'm just trying to get all this extra stuff out of the way so I can kind of focus. This one is at 0. This is at 4.5 volts. This one is at 4.5 volts. This is at 9 volts. This is at 0. This is at 9 volts. I've taken the charges away and just looked at the potential that each plate was at. If I suddenly flip this one, that would suddenly make the 0 plate and the 4.5 volt plate flip positions. Now, I don't know what the answer is here, but I know that this blue conductor would have to have a flow of charges until they were at the same potential. This green conductor would have to have a flow of charges until they were at the same potential. And this yellow conductor would have to have a flow of charges until they were at the same potential. I do not know what these potentials between the plates would be in order to satisfy that answer. And I do not know what the charges would be to satisfy that answer. I know that there would be a finite amount of available charge. So I would never ask this question because I'm not sure how to go about solving it yet. I'm sure if we spent a lot of time and were dedicated, we could probably figure out what to do here. But I don't think I think this is a little bit outside the bounds of what would be asked on an exam. And again, I couldn't tell you what's in parallel or series. That's not really an adequate way of describing this. Okay. I tried to thoroughly answer your question, even though your mom's in there, talking to you. So, there's been a lot of mom invasions today. There's a lot in second period too. There's a cat invasion in second period. Somebody actually brought a therapy cat to a kid in class. Like, wow, you're in physics. Here's a cat. I thought if somebody could bring you a therapy cat or a therapy puppy in the middle of physics, that would probably make physics a lot better, especially when you have to suffer through my class. So that was a lot of fun. I have no idea what time the bell rings. So does that get us someplace? Does that make sense about what would have to be done in order to figure out the answer? And I don't know how to do it. I'm not even sure where to begin. But I do know that the problems we're going to have are not like this, but they are problems where you'll have a setup like that. Something where you might have a system of capacitors, just like we described. Something like this, where there was a charge established at the beginning. A potential was applied to the plates here of, say, 9 volts, like we just discussed. And there was a situation where the charges had to settle and the voltages had to settle. And then they will change something. They will say, I added a dielectric here. How's that going to affect the system? Or I increased the separation distance of this capacitor. How is that going to affect the system? Those problems get asked. So, we do have problems where you will have more than just 2 capacitors, and they're going to manipulate one of them with the expectation that you can figure out what happens to the rest of the system based on that one. And so that is something we do need to be prepared to deal with. All right. What time does the bell ring?
Like
1 minute?
now? Yeah.
So our goal is to go over homework tomorrow. I don't believe there's anything I can teach you that isn't already in the homework. I think your homework I think we've covered all the material that's in the homework. You guys who have done most of it know that it's all there. I would like to have an opportunity to go over the homework tomorrow. Things are looking good. Perhaps we look at a quiz maybe early next week on this. Then we can start looking at some of the current flow stuff. I'd like to get into current flow before Thanksgiving. I think that'd be a good place to be. That means we can finish all the way through RC circuits by Christmas time. That would be my goal. You guys know that I would prefer to send you guys out to the Christmas break without any homework. Well, the holiday break without any homework. And I really want to live up to that goal. I don't want my family to be burdened with work over the break. I don't want your family to be burdened with work over the break. But to do that, we have to get all the way to RC circuits. So I'm going to throw an FRQ at you tomorrow. That's going to be basically homework for the weekend. That's going to show you what a capacitor question looks like on the AP exam. Okay? And that'll give us an idea of whether you guys are prepared for that or not. So did I give you a due date for the lab? What do you guys think? Tuesday, Wednesday of next week? That's sufficient amount of time? All right, so let's go with Tuesday of next week. All right. If you're having difficulty getting the lab done, let me know. All right, I'll let you go now. I got to go to my next class. It's down the hall. So take it easy. Of course, Abby's going to be there for it, but that's the way it is. Bye-bye, folks.
Bye,
Bye-bye.
Mr. Shelton.
Bye-bye. Have a nice day.
Mr. Shelton.
Bye. Have a good day.